This is 2.2, Limits Involving Infinity, Part 1. Your objectives for this lesson are to apply the Sandwich Theorem, determine asymptotes of a function, and apply properties of infinite limits. To introduce this topic, we're going to look first at the function f of x equals 1 over x. You see the graph of that over here. And as you can see, that as x goes to infinity, so as x tends to infinity, and that would be this way, infinity is the largest possible positive number. 1 over x, this red line, looks like it is approaching 0. So 1 over x becomes 0. And we can therefore conclude that the limit of this function as x goes to infinity actually is 0. And as x tends to negative infinity, so that would be the smallest possible number going this way, 1 over x becomes 0, and therefore our limit is equal to 0. So you can see that this line just kind of keeps going towards infinity. This is an infinite limit because it's going to infinity. And we can see here, and you might remember asymptotes from pre-calculus, that y equals 0 is a horizontal asymptote of the graph. So I could actually put a line on here. I'm going to do that. This line here, let's make it a dotted line, since it is an asymptote. This line is an asymptote because the red parts of this graph approach it. They will never reach it, they will never touch it. They're just going to get closer and closer and closer, but they're never going to touch it. So this is a horizontal asymptote of this graph. The definition of a horizontal asymptote is as follows. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. So basically, if your x value approaches the large number infinity or the very small number negative infinity, if it just keeps going at a certain value, then that value, that b, is your asymptote. So back here we have y equals 0. This 0 is our b. Okay, continuing on, we have f of x equals 2 plus 1 over x. So if you were to look at this graph, and let's do that, so let's pull it up. So y equals 2 plus parentheses 1 divided by x. Then you see basically the same graph we were looking at before, but it's been raised up 2 units. So we have the limit as x tends to infinity of this function is equal to 2. And you can see that if you were to start tracing and going towards positive infinity, the y values are getting closer and closer to 2. Your calculator, if you scroll out far enough, might actually say 2, and it'll just keep on being 2, but your calculator is not perfect and it has rounding issues, so don't be fooled by the calculator. Y never actually equals 2. And then if we were to scroll the opposite direction, so scrolling the opposite direction, you can see again the y values are getting closer and closer to a positive 2. So since this is a 2 and this is a 2, we definitely have one horizontal asymptote, or HA, at y equals 2. Example 1. We have f of x equals x divided by the square root of the quantity x squared plus 1. And we're just going to take a look at this graph really quickly. I already have a picture of this from the calculator here. And you can see that as x goes to infinity, so as we're traveling up this way, this is approaching y is approaching 1, okay? And as x approaches negative infinity, again this way, y approaches negative 1. So we have then two horizontal asymptotes, one at y equals 1 and one at y equals negative 1, because the horizontal asymptotes are where you have the infinite limits with x, okay? So here and here. We can also use the Sandwich Theorem to find limits as x tends to plus or minus infinity. So that will also work here. Example 2, find the limit as x tends to infinity of f of x for f of x equals sine x divided by x. So this graph is coming up again. Let's take a look at the graph. We want to solve this problem graphically first. So looking for a limit graphically first. Sine x divided by x. And let's adjust the window. I want to make it negative, negative 4 pi by 4 pi for the x's. And for y, we're going to make it negative 0.5, 1.5. Okay, there we go. So here is sine x divided by x. And I can see that as x is going out towards infinity, I'm kind of going back and forth between the x and y axis. You can see that I'm going back and forth between the positive and negative, closer and closer to the x-axis, and this holds true in both directions. So we are getting closer and closer to 0, even though we're oscillating, and the same is true in the other direction. So if we go back this way, you can see the same thing happening here. We're going up and down and getting closer and closer to y equals 0. So we get horizontal asymptote at y equals 0 because the limit as x goes to infinity of f of x equals 0. And also, we only need one to get the asymptote, but we have both. So I'm going to write both. To negative infinity, we get 0. Okay. Analytically, we know that sine x is always going to be between negative 1 and 1. So as long as x is greater than 0, this is for x greater than 0, we have negative 1 over x is less than or equal to sine x over x is less than or equal to 1 over x. And this is basically the top part becomes this. Okay, so we're going from this, and this is the top portion of your function, sine x. So putting the negative ones on top of an x, which is the same as the bottom. So therefore, by the Sandwich Theorem. So by the Sandwich Theorem, we know that 0 is the limit as x tends to infinity of -1 over x. And that is also the limit as x tends to infinity of sine x over x, which is the limit as x tends to infinity of 1 over x. So basically, since we already established the limit of 1 over x up here, that being 0, and negative x, you just have this flipped over. Those both have limits, horizontal limits at at 0. Sorry, those both have horizontal asymptotes at 0. So this graph will also have a horizontal asymptote at x equals 0. So the limit as x goes to negative infinity of sine x over x is equal to 0. Okay. The properties of limits as x go to plus or minus infinity are the same as those for finite limits. So the properties that we've already gone over hold true. That's talking about sum, difference, multiplication, the constant multiple, division, all those rules still hold up. And you can see them if you need more depth. That would be page 67 in your book. Okay. Example 3. We want to find the limit as x tends to infinity of 5x plus sine x divided by x. So we're going to use our limit rules here. And remember, if you have a plus sign in the numerator or a minus sign, you can break this up into two different fractions. So this is equal to this. Okay. And you can cancel out the x's here. Don't try to cancel out the x's here. This is sine of x. Sine is a function, so you can't cross those out. But we're left with 5 plus sine x divided by x. So now we have to find the limit as x tends to infinity of this. So the limit as x tends to infinity of 5 plus the limit as x tends to infinity of sine x divided by x. And we know that the limit of a constant is just the constant number, so 5. Plus, we just established the limit of sine x divided by x as x tends to infinity is 0. So your final answer here is that the limit of this function is 5. And that is it for part 1 of 2.2.